I just have to replace this by 5 and put in the calculator. I have no idea what I'm going to get. So all I have to do is just, I'm going to share my screen, go to this, and okay, so I have left parenthesis, e to power 5, and then minus e to power negative 5. You know me, I have to have parentheses everywhere. Just a habit. And divide by 2. I have no idea what this is. But this is how I enter it, because knowing that hyperbolic sine is e to the x minus e to negative x. In the same way, I will have natural log, but the natural log is easier. I want to explain this with the natural log. So whatever I get, so let me click on and copy it. So this is 74.203, and of course I have to be careful at what they are asking, how many decimal digits. Now, for this, here's what happens. So hyperbolic sine equals e to natural log 5 minus e to negative natural log 5 divided by 2. Well, there is a property. You don't have to do this. You can just plug it in. But there is a property that this equals 5. And the negative power will come, so negative 1 will become the power, and this will be 1 over 5. So basically, this is 5 minus 1/5 divided by 2. 24 over 5 times 1/2. So 12 over 5, or 2.4. But the calculator will give you the same answer. I just want, yes?
Last part with the negative ln?
Yes, let's talk about that. Very good. So only a to log base a of x is x. Sorry about that. So in other words, as long as this number is the same with this number, then the answer is x. Same thing with e raised to natural log x, because this number and the base here are both the same. A and A, E and E. So then the answer is x. But what happens now when I have a minus in front? I have to work on that, because here there is a plus. So if I have e to negative natural log x, first I have to write e to natural log. Remember, the number in front is the power, x to negative 1. And now the answer is x to negative 1. I can't have anything in front. In other words, I can, but only positive. For the answer, for the property to be applied and the answer to be x. So that's why first I have to get rid of this. And we know that whatever is in front, it goes in as a power. Or it comes from the power. One way or the other, it's the same thing. So if I write here negative 1, then I put the power in front. If I have negative 1, it comes back to the power. And now this is the answer. And that's how I got the 1 over 5. Because of the negative in front that goes back here. I just wanted to refresh your memory on these properties, but again, you can just plug in and get 2.4. Okay, so let's see a way of proving any of this. So let's start with this one, and then we'll go to that. So I'll replace cosine by this, I'll replace sine by this, I'll add them together, and I'll get that. So that's the easier. So let's do that together. So I have e to the x plus e to negative x divided by 2, which is cosine, plus, this is number 3, plus e to the x minus e to negative x divided by 2. And when I add them, I get, so this is the same denominator, right? So I have 2e to the x. These two go away, right? Because they're one negative and one positive. So divided by 2, and I get e to the x. Because e to negative x is positive here, and e to negative x is negative, so they will go away. Now the last one, so any questions on this one? Very good questions. Thank you so much. Is this okay? So basically what I'm saying here is when, oh, not that page, this page right here. So every time we look at hyperbolic sine, hyperbolic cosine, we always have to remember their definition. So this is the difference of two exponentials over 2, and this is the sum of the same exponentials over 2. So every time I see that, then that's what we need to do. So this was clear, and this I think is clear. Any questions? Anyone? Before we look at number 4. Everything okay? Yes? Anyone needs more time?
I think it's okay.
Okay, so now let's look at this one. So they're asking us to show that this is the case. Hy cosine x. So hyperbolic sine x, hyperbolic cosine x. This is the same property that we know for trig functions. So sine of x plus y is sine x cosine y plus sine y cosine x. It's exactly the same property. So in this case, all we have to do is just use exponentials. So it doesn't matter where you want to start. You can start here and show that it's this, but it's better if we start on this side with the right-hand side. Don't look at the left-hand side and see what we get. So we know that this is e to the x plus e to negative x over 2, and this is, careful, so xy, of course, xy. So this one is e to y minus e to negative y divided by 2. So hyperbolic sine, hyperbolic cosine. Hyperbolic sine and hyperbolic cosine. The other one will be reversed, but I want to have them exactly in the same order we have them. So hyperbolic sine, the minus, hyperbolic cosine with y, so it's with plus, and now plus. Hyperbolic sine with y, so e to y minus e to negative y divided by 2, and times, I'm going to try to squeeze it in here, and this is the same with x, but with positive. So e to x, e to negative x over 2. Okay. So as you see, they are very similar, but so it's 1/4. So e to x times e to y will be e to x plus y plus e to x times e to negative y will be e to x minus y. Negative e to negative x times e to y will be negative e to negative x plus y. And this times this will be negative e to negative x minus y. And since this is also 1/4, I'm just going to keep 1/4 outside and just continue. Plus e to y times e to x is e to x plus y. E to y times e to negative x plus e to negative x plus y. Negative e to negative y times e to x minus e to x minus y. Finally, this times this minus e to negative x minus y. Okay, we hope that something goes away, something, anything, please. So let's see. The negative x plus y and the negative x plus y minus in front, positive in front, please go away. Okay, anything else? Yes, x minus y, one with plus, one with minus. Yes, okay. Now these are 2. So 1/4 outside, 1 apple plus another apple, 2, e to x plus y. And these 2 are the same. Minus 2 e to negative x minus y. Okay. I will factor out a 2, and I'll get 1/2 e to x plus y minus e to negative x minus y. Okay, leave it alone. So this is the right-hand side. Now, I will look at the left-hand side. And sine, hyperbolic sine of x plus y is by definition e to x plus y minus e to negative x plus y. Then these two are identical. So this is the left-hand side. So the right-hand side was determined with a lot of calculations, but the left-hand side, so this is hyperbolic sine of this. Hyperbolic sine of this is e to this minus e to negative this over 2. But they are now identical. And we proved the identity. The left-hand side equals the right-hand side. Very good questions. Thank you. So that was number 4. It all reduces to manipulating these expressions. This one for sine and this one for cosine. Thank you for asking, and thank you for asking all these questions, because as you know, there is no way I can show each and every type of problem in class. I wish I could. Great. Anything else? Anything else you worked on? Anything else you'd like to see? Anything? And did you need more time on this? Anyone?
Yeah. Can you explain again in the end when you said they're identical? You're comparing.
I'm comparing the right-hand side that is simplified to this. The right-hand side, all this, is simplified to this. So we started by replacing each piece. We multiplied, we did our utmost. We couldn't go any further. And then I said, fine, this is it. But now I have to look at the left-hand side. And when I apply this to the regular e to the x minus e to negative x, this is what I get. And this is identical with this.
Thank you.
Better?
Yeah, thank you.
Thank you. Do I still need it here?
Yeah, I'll just take a picture of it really quick.
Sure. I will also post this.
All right, I got it. Thank you.
Perfect. Other questions for me? Anything else? Okay, we would like to talk about the last section of this chapter, because 3.11 was done. So the last section of this chapter, I know we only have about 25 minutes. I'll try. I don't think we can finish it, but that's okay. So first, I'd like to talk about something called differentials. The second half is about linear approximation.
Christine wrote in the chat.
Yes. Yes. Let's see. Christine, are you okay? Yes. Yes. Yes, Christine. I think you are muted. Yes. We cannot hear you, but can you tell us what, do you have a question on this or? Okay. You can email me and I will look. Okay. So the other half of this section deals with linear approximations and linearization of a function. So this is part 1, and this is part 2. I'll start with part 1. If we have time, I'll get to part 2. If not, we'll leave this for Wednesday. Okay, so some time ago, we looked at this function several times, actually, in which we had a point P and we had a point Q, and we said that Q is very close to P, but I'm zooming in so I can explain what differentials are all about. So, of course, this is x, and I remember you told me that that was f of x, so of course this is our function. And of course, if you remember, this was x plus h. We are changing the notation, but the meaning is the same pretty much. X plus dx instead of h, or x plus delta x, and you can say another delta. Yes, this is one delta, and this is a different delta. This is the uppercase delta, this is the lowercase delta. And of course, this is our dx equals delta x. A tiny bit. So I'm going to explain the notation first. Delta x is the change in y, change in x, of course. Change in x. What is dx? Same thing. In this case, they are the same, but this notation is the differential of x. So this is the exact change in x, a tiny bit change because q is right here, right? Q is here, but I'm zooming in. So dx is a small number equal to delta x. This is the actual change in x. Why is this called different? Why is it called a differential? Why isn't it called just a change in x? Because it involves the derivative. Or if you want, it's connected to f prime. That's why we call it a differential, dx. We don't call it a change in x, but they are the same. Okay. Now, of course, this will be f of x plus delta x, the same with f of x plus dx. First thing we are going to look at is this difference between f of x plus dx and f of x. This is called delta y, and I'm going to explain what that means. So delta y is the exact change in y, or the function, for a change or triggered by a change of delta x in x. The exact change. And that is delta y. So by definition then, delta y is f of x plus dx minus f of x. Delta x minus f of x. Since we're using delta, I have to use delta in here. Although you can say, but why don't you write dx is the same thing? True. But when we're looking at delta, so what does this mean? Well, okay, so forget about this function. So let me explain what it means. And we'll come back to the function. I haven't finished there. Okay, so let's say I have a disk. And the radius of the disk should be 10 inches. Instead, the actual is 10.1 inches. It means that there is an error of 0.1 inch. This is the delta x. This is the error or the change in the radius. It should be 0. Should be no change, no difference. It should be exactly 10. but it's not. It's 10.1. The radius is 10.1. So then delta x, the change in x, or the error in x is 0.1. What is the problem now? The problem is that this change or error in x, in other words, in r, I can even write the dr to be exact, because we're talking delta r, because we're talking about r. Well, this will trigger a change in the area. So the area is pi r squared, and it should be 100 pi, whatever, inches squared. But now it's not going to be, because this error in the radius will give us another area. Okay, it will give us a area of r plus 0.1. So that will be 100 times 10.1 squared. And what is the actual error in the area? It will be this minus this, or this minus this. So this is the problem. When there is a minor error in the x, we will trigger an error in the function. If there is no error, then I don't have delta A. But there is an error in the radius, therefore, there will be an error in the area. So, in other words, this is the radius of the disk. This is the function that gives the area. So the error in the radius of the disk will create an error in the area of the function. The area of the disk, the function itself, delta y. Okay. Fine. So now we know what delta x is, dx, delta y, and what is the meaning of all this. Fine, but we're not finished. At this point, I am going to draw the tangent to the graph of f of x at P. I am going to extend it. I'm also going to extend this vertical line through Q. And I'm going to form this triangle. Remember, again, Q is here. So all this is very tiny, very tiny, tiny. Okay. So at this point, I know that this is delta y. I am focusing now on this distance between this point and this point. I want to talk about this distance now. So if we look at this right triangle, can anyone give us the slope of this line in two different ways? So forget about the triangle for a moment.
I have a question. What do you mean, like, in two different ways?
Okay, that's what I said. So forget about this for a moment. I have a function, I have a point, and I have the tangent to that point, to the graph of the function at that point. Can anyone give us the slope of this line, knowing that the x-coordinate is x, based on what we know so far from calculus?